నమస్కారం. డాక్టర్ బిఆర్ అంబేద్కర్ సార్వత్రిక విశ్వవిద్యాలయ విద్యార్థులకు స్వాగతం.
Good morning, students. The title of today's lesson is Point-Wise and Uniform Convergences. This is taken from Unit 10 of your course material BS317 MAT E of Reanalysis course of your third semester BSc second year. Well, first of all, we will learn what a real sequence is, and then we look at its limit concept. In your first semester, you have learned the concept of limit f of x as x goes to a is equal to L. There, f x is a real valued function of real variable x, and a is a limit point of the domain of f. Today, we will define what a real sequence is, and then we will define its limit. In fact, we will define the concept of convergence of a real sequence, and then in that case we can define limit x n as n goes to infinity to be the limit to which that sequence converges. First, let us start with some examples. If you look at this expression 1 1 1 1 and so on, taken indefinitely and infinitely, this kind of an expression is called a real sequence. Here these entries 1 1 1 are called entries or members or elements, and this is called a sequence. These are real numbers, so this is called a real sequence. And another example is 1 2 3 and so on, n and so on. Here the nth term, 1 is first term, 2 is second term, 3 is third term, the nth term is n. These are the natural numbers, and this thing is also called a sequence, and you may give a name to this sequence yn starting with n equal to 1 to infinity. We put yn in curly brackets and write n equal to 1 as suffix and infinity as superfix, and this symbol is name for this sequence, and this is not equality, but it speaks about the notation of this expression or string to be this symbol. And another example of a sequence is 1 half, 1/3 and so on, 1 by n and so on. Here 1 means 1 by 1, second term is 1 by 2, third term is 1 by 3. So, for the nth term, the nth term will be reciprocal of n, where n is a natural number. Here when we want to define a sequence, we have to define the nth term precisely. So, that is what we are trying for. Here in this sequence the nth term has been n, here in this sequence the nth term is 1 by n, n is a natural number, and we are giving name Zn n equal to 1 to infinity as name for this sequence. So, in general we have real sequences x n n equal to 1 to infinity. This x n becomes a function. In fact, if x is a function from the set of natural numbers into the set of real numbers, it takes every natural number small n to some value x of n, some real value. Give nth symbol for x of n to be x suffix n. So, whenever we have a function like this can be expressed, a function is determined by its range values. So, it is determined by x n values. So, instead of speaking about this function, we express it in terms of its range values. The range values are x1, x2, x3 and so on. So, that we denote by xn. For that we give the symbol xn n equal to 1 to infinity. So, whenever we have a function x from the set of natural numbers in the set of real numbers, we have a real sequence x1, x2, x3 and so on. For example, if you take this expression 1 2 1 2 1 2 and so on, here if this is first term is 1, second term is 2, third term is 1, fourth term is 2. So, odd number terms are 1s, even number terms are 2s. So, x 2n plus 1 is 1, x 2n plus 2 is 2. So, like that we can define the corresponding nth term or 2n plus first term or 2n plus second term. So, So, this also is a real sequence. Well, our objective of today's lesson is to know about point-wise convergence of sequences of functions and uniform convergence of sequences of functions. So, first of all, we look at the convergence of a sequence of real numbers. Say we have a sequence x n equal to 1 to infinity. For that, if L is a real number, we say limit x n as n goes to infinity is L, if and only if this statement is true. That is, for any arbitrary positive epsilon, there must be a natural number n naught such that for all n greater than or equal to n naught, the distance between x n and L must be less than epsilon. It means, this essentially means that leaving a few values of n's, all other xn's must be within a distance of epsilon from L. Means, if you take a sequence xn, you have values x1, x2, x3 and so on, and you take an arbitrary positive value epsilon. For that epsilon, correspondingly, if you can choose a natural number n naught such that the suffix values of xn's, that is n's, if they are greater than or equal to n naught, the corresponding xn values must be at a distance of epsilon, at the most at a distance of epsilon from L. They must be within a distance of epsilon from L. Here here in this definition, all the remaining x1, x2 up to x n naught minus 1, n naught minus 1 values of xn's, they need not be in this epsilon neighborhood of L. So, and this must be true for every epsilon positive. If this is the case, we say the sequence xn converges to the limit L, and we say the sequence xn is convergent, and we write limit xn as n goes to infinity is equal to L, and we call L a limit of the sequence xn. In today's lesson, we replace these real numbers xn's by functions. Instead of a sequence of real numbers xn n equal to 1 to infinity, we take a sequence of functions fnx from n equal to 1 to infinity. These fn's are functions. When we speak of functions, they must have some domains, and we take these fn's as that they have common domain. And so, we let this x vary over a common domain S, where S is a subset of real numbers and non-empty. Such a sequence is called sequence of functions. Let us look at some examples. 1 x, x square, x cube and so on, n plus first term is x power n and so on. This is geometric series. Initial term is 1 and common ratio is x. We know this is convergent if mod x is less than 1. If x values lie between minus 1 and 1, we can show that this sequence is convergent. That is, this statement is true whenever x values lie between minus 1 and 1. We want to define the convergence of sequence of real valued functions. So, in this x, the point x varies over a domain S, where S is a subset of R and S is non-empty, and in that set S, let us take a particular point small a, right. For example, if we take the function sequence to be x power n, that is our fn x is x power n. This is geometric series function, geometric sequence function. Then if we take a particular value from the open interval minus 1 1, I am taking one a value in this open interval minus 1 1, means a is greater than minus 1 and less than 1, and correspondingly I am concentrating on this, the corresponding sequence. I am substituting x equal to a in this, I get a power n equal to 1 to infinity. This is geometric sequence. 1, I get a, in fact if I take n is from 0 to infinity, I get 1, 2, I get 1 a square, a cube and so on, a power n and so on. So, that is geometric sequence. Whenever a is non-zero, it is well defined. So, and we know that because mod of a is 1, we know limit a n as n goes to infinity is 0, and means this sequence converges to the value 1. we say this sequence xn of functions from n equal to 1 to infinity converges to 0 pointwise. Pointwise means we have taken the value a equal to 0, we have taken the value x equal to a, and there limit of xn is becoming 0, and we say xn tends to 0, xn converges to 0 pointwise at the point x equal to a, right. And well, let us look at let this a vary over S and see how we can define the pointwise convergence of a sequence of functions f(n)x at that point x equal to a. Let fn be a sequence of functions defined on a subset S of R where S is non-empty. From in S, let us take a point small a, and let f of a be a real number, and we can evaluate these functions fn's at x equal to a. We get fn of a. So, fn of a's are real numbers and f of a is a real number, and so fn of a form a sequence of real numbers, and we can speak of the convergence of the sequence of fn's fn of a's to f of a. And if this statement, that is for every epsilon positive there exists n naught belonging to n such that for all n greater than or equal to n naught the distance between fn of a and f of a is less than epsilon. If this statement is true, we say the sequence fn a converges to f of a. Means in this epsilon neighborhood of f of a, all the fn a values fall except leaving a few values of fn's for n equal to 1 to n naught minus 1. Leaving n naught 1 minus 1 values, all other values of fn a's must fall in this epsilon neighborhood of f of a, and this must be true for every epsilon. If this happens, we say the sequence fn of x converges to f of x at x equal to a, and we say this convergence is positive. We also write, and if this point a is varying over S and if all fn of a, all the corresponding fn of a's converge to a suitable numbers f of a's, we say fn of a converges, we say fn converges to f pointwise on S. Here the n naught we are coming across is this n naught depends on epsilon and a, and so we say this convergence is pointwise convergence, and the crux of this convergence is that this n naught depends on the values of epsilon and x or a. Let us look at an example. Let us consider the functions fn of x equal to x by n. Here n is a natural number, that is 1, 2, 3 and so on, and x is a real number, and therefore we get sequences of functions, and as n goes to infinity, we know x by n goes to 0. So, we may expect fnx converges to 0 function, and so if you take x equal to a, you have fn of a minus f of a, if fn of a becomes a by n, and f of a, because we guess our f of a becomes 0. So, we guess this f of a becomes a limit. So, let us take f a equal to 0, and let us study this. We have a by n minus 0, it simplifies to a by n, and we are taking modulus, and from here we calculate n value and bring epsilon to the other side, take n to the other side. We have n is greater than modulus of a by epsilon, and here we take its integral part, and we may take one more than that, and we may choose n naught to be larger than or equal to this. So, whenever our n's satisfy greater than or equal to n naught, then we will have n is greater than this. So, it gives this, and from here, from that we get modulus of a by n is less than epsilon. So, x by n, fn of a's or a by n, they are converging to 0. They are converging to 0. Here the choice of n naught is depending on a and epsilon, right. It is this is n naught. So, it is depending on a and epsilon, and we have a by n is converging to 0, and a may vary over the entire real numbers. So, our fn of x are converging to the 0 function, and this we write limit fn as n goes to infinity is equal to 0 pointwise. This is here you can as well write fn x means x by n, and and in some situations you may have functions like this, f(n) of x n equal to 1 to infinity. You have cos nx by n, that is your f(n)x, and you have its modulus equal to 1 by n. As n goes to infinity, this goes to 0, and 1 by n is independent of x, and therefore this f(n)x converges to 0, but here n it does not depend on x. So it depends on n epsilon alone. So here cos nx by n converges to 0 pointwise, and in fact here, because n not depends only on x, n not depends on only on epsilon, we say this kind of convergence is uniform convergence. So again we take a sequence of functions fn's, and each fn is defined from S to R, is defined, right, fn is a function from S to R, and we may ask we ask for the convergence of fnx. X is varying in S, x is a point in S, so fn of x is a sequence of real numbers, and let f be a function from S to R. So say fn x and fx are satisfying this statement, means for every epsilon positive there exists a natural number n naught such that for all n greater than or equal to n naught, mod fnx minus fx is less than epsilon, and for all x belonging to S. Means here this is epsilon neighborhood of f of x. In this, all fnx are falling, leaving a few values of n's, and this statement is simultaneously true for all x values. Means this property of convergence is displayed uniformly throughout the subset S, and therefore this kind of a convergence is called uniform convergence. And if whenever this statement is true, we write limit fn as n goes to infinity is f uniformly, and if it is pointwise, we wrote it is limit f of n as n goes to infinity is equal to f pointwise, and pointwise convergence comes when you take x equal to a here, and here in uniform convergence our x can be all points in S, and therefore and for pointwise convergence you have to take x equal to a. So the pointwise convergence is a particular case of uniform convergence, and in fact uniform convergence is stronger than pointwise convergence, and means uniform convergence implies pointwise convergence, and if you take its contrapositive, we get not pointwise convergent implies not uniform convergent. So if you have a sequence of functions which are not pointwise convergent, then that sequence is not uniformly convergent. And if we look at the geometric meaning, this is an epsilon neighborhood of f. This graph is that of f plus epsilon, this graph is that of f minus epsilon. If fn values fall, this is the graph of fn. If the graph of fn falls between the graphs of f minus epsilon and f plus epsilon, means leaving a few values of n's, our function the functions fn will be converging to f uniformly. Let us look at an example. We can see we can consider fnx is equal to x square e power minus nx, and for a fixed x, and here n is positive, right, and in fact our set SC is a set of all non-negative real numbers 0 to infinity, and therefore for a value x in this, x square into e power minus x, so this goes to 0. So we can see that this sequence converges to 0 pointwise. In fact, we can obtain that this sequence converges to f, that is the 0 function, uniformly. Well, if we want to check whether a function is not uniformly convergent, means the negation of this statement must be true. Means what is negation of this statement? Negation means for every epsilon becomes greater, there exists. So the negation of this statement is that there exists epsilon positive, such that there exists becomes for every epsilon. For all n naught, correspondingly there must be n x n naught such that means whatever nk you take, there must be x and k in S, as that this fails, means mod fnk of xk minus fxk must be greater than or equal to epsilon. If the negation of this statement is true, we get that the sequence fn does not converge to f uniformly. So, let us look at an example. In fact, the negation of the definition of the uniform convergence gives this statement, the lemma of this statement, means fn's are functions on S, and the sequence fn is not uniformly convergent to a function f from S to R if and only if there is a sequence, there is a subsequence fnk where k equal to 1 to infinity of fn, such that there is a sequence xk k equal to 1 to infinity in S, such that there exists an n epsilon naught such that for every k in n, the distance between fnk of xk and f of xk is greater than or equal to epsilon naught. So, if we can obtain that this statement is true, the corresponding sequence fn does not converge to f. So, to check if a sequence fn is not converging uniformly to f, we must be able to produce xk and nks. Let us see what it's with some examples. Fnx is x by n. So, for these fn's, if we take xk equal to k and nk equal to k, nk always has to be k, nk equal to k, then fnk of xk becomes, it is xk by nk, xk is k, nk is k. So, this is 1. So, and as n goes to infinity, x by n tends to 0. So, these tend to 0 pointwise, tend to the 0 function pointwise. So, which and if we take the modulus of fnk of xk and f of 0, it is, this being 0, modulus of this is 1. So, and epsilon naught is 1. So, these xk and nk values and epsilon naught value show that the negation of the statement of the definition of uniform convergence is true, means the sequence fn is not uniformly convergent to the 0 function. In this lesson, we looked into the concepts of real sequences, their convergence, and then we looked at sequences of functions and their pointwise convergence and uniform convergence. We studied some examples and saw that uniform convergence is a stronger property implying the weaker condition pointwise convergence. Thank you.
మా కార్యక్రమాలపై మీ సూచనలు సలహాలు తెలియచేయండి. మీ సూచనలు సలహాలు తెలియచేయవలసిన మా చిరునామా: డైరెక్టర్, ఆడియో విజువల్ ప్రొడక్షన్ అండ్ రీసెర్చ్ సెంటర్, డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ, ప్రొఫెసర్ జి రామరెడ్డి మార్గ్, రోడ్ నంబర్ 46, జూబ్లీ హిల్స్, హైదరాబాద్ 500033.